Hi everyone, my name is Huynh. Today I would like to present our paper, Optimal Beam Association in Millimeter Wave Vehicular Networks with Parallel Reinforcement Learning. My presentation today is divided into 4 parts. First, I will give some background information and the motivation that lead us to this research. Then I will discuss about the system model and the problem formulation. After that, I will present our proposed solution. Finally, I will highlight some simulation results. As you know, intelligent transportation and vehicular communication offer a great potential to enhance traffic efficiency, improve road safety, and enable disruptive entertainment services as well as autonomous driving. However, the services often requires low latency, high reliability, and extremely high data rate. It is expected that a vehicle may produce 1 terabyte of data in a single chip. Hence, conventional communication technology may not be feasible for future vehicular networks. Millimeter wave communication has been recently emerging as a very promising solution to support vehicular networks. Different from conventional wireless communication, the millimeter wave technology operates at much higher carrier frequency, from 30 GHz to 300 GHz. Hence, it can provide much more spectrum resources, resulting in high data rates and low latency communications. However, the millimeter wave technology has several drawbacks, such as high propagation attenuation, selective directivity, and susceptibility to blockage. Consequently, the millimeter wave channel quality is usually degraded, especially in vehicular communication under high mobility. Several studies in the literature have been proposed to address the limitation of millimeter wave communication. However, the solution did not account for the high mobility of vehicles and the dynamics of the environment. More importantly, they require complete information about the environment in advance, which is not feasible in practice. A few works introduce online learning-based solutions to deal with the drawbacks. However, the effect of the high mobility and blockage on beam association has not been considered. In this work, we developed an optimal beam association framework for millimeter wave vehicular communication under the high mobility of vehicles and the uncertainty of blockage. In particular, we first use the semi-Markov decision process to formulate the system. Then, a lightweight yet very effective parallel learning algorithm is proposed to obtain the optimal beam association for vehicles in the system. Next, I will present our system model. In this paper, we consider a millimeter wave vehicular network with an LTE in node B and a set of millimeter wave base stations. Each vehicle will have one LTE interface and one millimeter wave interface. The LTE interface is used to communicate with the node B, and the millimeter wave interface is used to communicate with millimeter wave base stations. When a vehicle leaves a beam or moves to a blockage zone, the receive signal strength indicator RSSI will drop. Hence, the vehicle will not be able to communicate with its current connected base station. In this case, the vehicle needs to connect to another beam, which provides better channel quality. This beam can belong to the current connected base station, or it can belong to another millimeter wave base station. Conventional approach usually makes a beam association decision based on the current channel information or network state. However, the solution may lead to too frequent handover due to the intermittent connectivity of millimeter wave link. Differently, our algorithm can learn from multiple vehicles on the road simultaneously to obtain the RSSI profile of the beam in the system, and in this way we can reduce the number of beam associations and handovers. To capture the dynamics of blockage, channel quality, and mobility, we first model the problem at a semi-Markov decision process at MDP. Different from the conventional MDP, in the NMDP, an action is only taken when an event is triggered. This makes the NMDP framework more effective in capturing the dynamics and uncertainty of the environment. In the NMDP, we need to define the state space, the action space, and the immediate reward function. So in this work, we define the state space as the current ISSI level and the current connected beam. As you can see in this equation, we have L is the ISSI level, and B and K is the current connected beam, in which N is the ID of the mmWave base station, and K is the beam ID. In this work, an event is triggered when the vehicle moves to a new location. In this case, the InnoB decides if the vehicle needs to associate to a new beam or stay on the current beam. In this way, we can define the action space as shown in this equation. A is the action made as state as A equal to B and K if the InnoB guides the vehicle to connect to beam B and K, and A equal to B 0, 0 if there is no available beam at the current location. In this paper, we aim to maximize the long-term average data rate of the vehicles, so that we define the immediate reward after performing an action at the data rate that the vehicle can communicate with the mmWave base station. Note that the data rate depends on the current ISSI level, which is random and fluctuates corresponding to the condition of mmWave links and the environment. However, our learning algorithm can learn the environment parameter to obtain the optimal beam association policy for the vehicle. To obtain the optimal beam association policy, the Q-learning algorithm is often adopted. However, the Q-learning algorithm is well known for its slow conversion rate, especially in dynamic and complicated environments as considered in this paper. To that end, we developed a lightweight parallel Q-learning algorithm to quickly obtain the optimal policy by learning from multiple vehicles at the same time. As you can see in this figure, the vehicle on the road can act as active learner to help the system to collect experience. Based on the experience, the proposed parallel Q-learning algorithm can quickly learn the environment information such as ISSI profile, beam location, vehicle velocity, and blockage. In this way, the parallel Q-learning algorithm can obtain the optimal beam association policy much faster than conventional Q-learning algorithm. At each decision epoch, the current vehicle chooses to connect to a beam and observe the data rate of the connected beam as well as the next state of the environment. Then the observations are sent to the InnoB for learning by the corresponding learning process to update the global Q table by using this Bellman equation. In this equation, gamma is the scale factor that presents the importance of future rewards. Tau t is the learning rate at decision epoch t. The learning process of each vehicle is independent from the others. All the learning process share the same global Q table. In this way, the Q table can be updated with more experience from multiple vehicles running on the road, resulting in a high conversion rate. Next, I will highlight some simulation results. In this paper, we compare our proposed solution with two other solutions. The first solution is migrate. This solution first explores all available beams at the current location. Then the beam with the highest ISSI level will be selected to connect. Once migrate selects the best beam, it will keep connecting to this beam until the end of the current decision epoch. This scheme is used to show the performance of non-adaptive and greedy solutions. As in mmWave system, the channel quality is not stable, so that the best beam at the current time may become worse at a later time. As a result, the performance of this solution may not as good as our proposed solution. The second solution is upward bound. So this scheme is assumed to know the knowledge about the blocking probability of all available beams in the current location. Then the beam with the lowest blocking probability will be chosen for the vehicle to connect. This beam is adopted to show the optimistic upper bound of the system performance. In this figure, we vary the mean speed of vehicles running on the road and evaluate the average data rate, the disconnection time, and the number of handovers. As can be seen in figure 1a, when the speed increases, the average data rate of vehicles decreases. This is stemmed from the effect of vehicle mobility on the handover process. In particular, if the vehicle speed is high, it may move to another beam before the handover process is completed. So this leads to a low data rate as the vehicle now needs to perform the handover again. Note that the data rate obtained by our proposed solution is higher than that of Markov's scheme and close to that of the upper bound scheme. In addition, when the vehicle speed increases, the number of handover under our proposed solution is reduced to avoid the negative effect of mobility, as shown in this figure. Differently, other schemes do not reduce the number of handover as their policy is fixed and they cannot learn the environment parameters. Note that the number of handover increase for all schemes when the mean speed is higher than 7 meters per second. The reason is that at very high speed, the vehicle may move to another beam before completing the handover process, and then it needs to perform the handover process again. Next, we vary the handover time and observe the performance of the proposed solution. Obviously, the disconnection time increases when the handover time increases, resulting in the decreasing of data rate of all schemes as shown in figure 2a. Again, our proposed solution achieves better performance than the Markov scheme and close to the upper bound solution. This is because the learning algorithm can learn and reduce the number of handover when the handover time is high. In particular, when the handover time increases from 0.1 second to 0.5 seconds, the number of handover obtained by our proposed solution is reduced, as the learning algorithm can adjust its optimal policy when the time for handover is high. However, when the handover time is higher than 0.5 seconds, the number of handover increases. The reason is that when the handover time is too high, the vehicle may move to a new zone before completing the handover process. And in this case, the vehicle needs to perform the handover again to keep its communication. However, our proposed solution obtains the lowest number of handover compared to other schemes thanks to the advantage of our learning algorithm. In figure 3, we compare the conversion rate of our proposed algorithm with the conventional Q-learning algorithm. It can be seen the proposed parallel Q-learning algorithm can convert to the optimal policy in less than 1,000 iterations, while the Q-learning algorithm needs more than 40,000 iterations to convert to the optimal policy. The reason is that the parallel Q-learning algorithm can learn from multiple vehicles at the same time. In this way, the global Q table can be updated with more experiences, resulting in high conversion rate. This is the end of my presentation. Thank you for your attention.